Imagine standing in your backyard on a clear night, gazing up at that faint band of light stretching across the sky. That ethereal glow you're seeing is our home galaxy, the Milky Way, containing over 100 billion stars, countless planets, and mysteries we're only beginning to understand. But what if I told you that somewhere out in the vast cosmos, there exists a galaxy so monumentally massive that it makes our entire Milky Way look like a grain of sand next to a basketball? Tonight, we're about to embark on a mind-bending journey through space and scale that will fundamentally change how you think about our place in the universe. We're going to compare our cosmic neighborhood to the largest galaxy ever discovered, and trust me, the numbers we're dealing with are so staggering that your brain might actually struggle to process them. I've spent weeks diving deep into the latest astronomical research, consulting with astrophysicists, and analyzing data from the most powerful telescopes humanity has ever built. What I discovered will blow your mind. We're talking about a cosmic giant that contains over 100 trillion stars, spans distances that light itself takes millions of years to cross, and harbors secrets that could rewrite our understanding of how the universe actually works. But here's what makes this comparison absolutely fascinating. It's not just about size. When you start digging into the details of these two galaxies, you uncover a story about cosmic evolution, the birth and death of stars, and the invisible forces that shape everything we see in the night sky. By the end of this video, you'll never look at the Milky Way the same way again. Let's start with what we know about our own galactic home. The Milky Way is what astronomers classify as a barred spiral galaxy. And when I say barred, I'm not talking about your local pub. I'm referring to that distinctive elongated structure of stars that runs through our galaxy's center like a cosmic backbone. Picture a pinwheel firework spinning in slow motion, except instead of sparks, you've got billions upon billions of stars creating those magnificent spiral arms that curve outward from the central bar. Our galaxy measures approximately 100,000 light-years across. Now, to put that in perspective, light travels at 186,000 miles per second. That means in 1 year, light covers about 6 trillion miles. So when we say the Milky Way is 100,000 light-years wide, we're talking about a distance of roughly 600 quadrillion miles from edge to edge. That number is so large that it becomes almost meaningless to our everyday experience. But stick with me because we're just getting started. The Milky Way contains somewhere between 100 and 400 billion stars. Why such a huge range? Well, counting stars in a galaxy is like trying to count grains of sand on a beach while standing in the middle of it. We can make educated estimates based on the brightness and mass of different regions, but getting an exact count is practically impossible with our current technology. What we do know is that these stars aren't randomly scattered throughout space like confetti thrown into the air. They're organized into distinct structures that tell the story of our galaxy's formation and evolution. The most obvious structure is those spiral arms I mentioned earlier. Our solar system sits in what's called the Orion Arm, sometimes known as the local arm, which is actually just a minor spiral arm between two major ones. It's like living in a cosmic suburb between two major highways of stars. The two main spiral arms are the Perseus Arm and the Sagittarius Arm, and they contain some of the most active star-forming regions in our entire galaxy. But the real powerhouse of the Milky Way lies at its center. Deep in the heart of our galaxy, hidden behind clouds of dust and gas, lurks a supermassive black hole called Sagittarius A star. This cosmic monster has a mass equivalent to about 4 million of our suns, and it's constantly feeding on surrounding matter while simultaneously shaping the orbital patterns of stars throughout the entire galaxy. The gravitational influence of this black hole extends for thousands of light years in every direction, acting like an invisible anchor that keeps our entire galactic structure from flying apart. Surrounding the main disk of the Milky Way is something called the galactic halo, a roughly spherical region that extends far beyond the visible edges of our galaxy. This halo contains some of the oldest stars in the universe, organized into clusters that formed when the cosmos was still young. These ancient stellar populations hold clues about the early history of galaxy formation and the chemical evolution of matter in the universe. The Milky Way also has a complex ecosystem of smaller satellite galaxies orbiting around it like cosmic moons. The most famous of these are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere. These irregular galaxies are slowly being torn apart by the Milky Way's gravitational pull, creating streams of gas and stars that will eventually be absorbed into our galaxy's structure. Now, as impressive as all of this sounds, and it really is mind-boggling when you think about the sheer scale we're dealing with, the Milky Way is actually considered a fairly typical large galaxy. It's bigger than most galaxies in the universe, but it's nowhere near the upper limits of what's possible. In fact, astronomers have discovered that our galaxy sits right around the median size for spiral galaxies in the local universe. This is where things get interesting, because when we start looking beyond our local group of galaxies, we begin to encounter cosmic structures that dwarf anything in our immediate neighborhood. The universe contains galaxy clusters, superclusters, and individual galaxies that make the Milky Way look absolutely tiny by comparison. But before we dive into the cosmic giant that makes our home look microscopic, we need to understand something crucial about how galaxies actually form and grow. This isn't just about random accumulations of stars scattered throughout space. Galaxy formation is one of the most complex and violent processes in the universe, involving dark matter, primordial gas clouds, stellar nurseries, and gravitational interactions that span billions of years. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly throughout space. But tiny density fluctuations, probably seeded by quantum mechanical effects during cosmic inflation, began to grow under their own gravity. Dark matter, which makes up about 85% of all matter in the universe, formed the scaffolding upon which normal matter could accumulate and eventually form the first stars and galaxies. The process of galaxy formation is still happening today. Galaxies grow by accreting material from their surroundings, merging with smaller galaxies, and sometimes colliding with galaxies of similar size. These cosmic collisions might sound catastrophic, but they're actually a normal part of galactic evolution. In fact, the Milky Way is currently on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. Don't worry though, this cosmic crash won't happen for another 4.5 billion years, and when it does occur, the vast distances between individual stars mean that actual stellar collisions will be extremely rare. What determines how large a galaxy can grow? The answer lies in the complex interplay between dark matter halos, gas accretion, star formation, and feedback processes from supernovae and active galactic nuclei. Larger dark matter halos can capture and retain more gas, leading to more star formation and bigger galaxies. But there are limits. At some point, the energy output from star formation and black hole activity can actually drive gas away from the galaxy, limiting further growth. This brings us to the absolute monsters of the galactic world. While most galaxies in the universe are relatively small, containing just a few billion stars, there exists a class of galaxies so massive and so large that they challenge our understanding of how cosmic structures can form and evolve. These are the giant elliptical galaxies, often found at the centers of massive galaxy clusters, where they act like cosmic vacuum cleaners, continuously absorbing smaller galaxies and growing to truly enormous sizes. The largest of these galactic giants is so massive that it contains more stars than thousands of Milky Way galaxies combined. It's a structure so vast that light takes longer to cross its diameter than our entire solar system has existed. When astronomers first discovered this cosmic leviathan, they had to double and triple check their measurements because the numbers seemed almost impossible to believe. This galactic titan doesn't just dwarf the Milky Way in terms of size and mass. It represents a completely different type of cosmic environment, with physical processes and structures that simply don't exist in smaller galaxies like our own. The gravitational forces at work in this monster galaxy are so intense that they can strip entire star systems from passing smaller galaxies, adding them to an ever-growing collection of stellar prisoners. But size isn't the only thing that makes this cosmic giant fascinating. Its very existence raises profound questions about the fundamental nature of galaxy formation and the limits of cosmic structure. How did something this massive manage to form in the age of the universe? What does its existence tell us about the distribution of dark matter on the largest scales? And perhaps most intriguingly, what would it be like to live in such a galactic environment? The answers to these questions will challenge everything you think you know about galaxies, stars, and our place in the cosmic hierarchy. We're about to explore a realm where the familiar rules of our galactic neighborhood no longer apply, where the very concept of distance takes on new meaning, and where the night sky would look utterly alien to human. Prepare yourself for a cosmic revelation that will shatter your understanding of scale in the universe. The galaxy we're about to explore is so incomprehensibly massive that when astronomers first detected it, they thought their instruments were malfunctioning. This galactic behemoth goes by the designation IC1101, and it's located roughly 1 billion light-years away in the constellation Virgo. But calling it simply the largest galaxy ever found doesn't even begin to capture the mind-melting reality of what we're dealing with here. IC1101 spans an incredible 6 million light-years from edge to edge. Let that sink in for a moment. Remember how I told you the Milky Way is 100,000 light-years across? Well, you could fit 60 Milky Way galaxies side by side and still not match the diameter of this cosmic monster. If our galaxy is a grain of sand, then IC1101 is a beach ball sitting next to it. The scale difference is so extreme that it borders on the absurd, but the real kicker comes when we start talking about stellar population. While our Milky Way contains somewhere between 100 and 400 billion stars, IC1101 is estimated to harbor over 100 trillion stars. That's not a typo. We're talking about 100 trillion individual suns, each potentially hosting their own planetary systems, all gravitationally bound within a single galactic structure. To put this in perspective, IC1101 contains more stars than there are galaxies in the observable universe. Now here's where things get really wild. IC1101 isn't just big, it's fundamentally different from spiral galaxies like our own. This cosmic titan belongs to a class called giant elliptical galaxies, and they operate according to completely different rules than the structured, organized spiral arms we see in the Milky Way. Instead of the elegant pinwheel pattern that characterizes our home galaxy, IC1101 appears as a massive, roughly spherical blob of stars with no discernible internal structure. The formation story of IC1101 reads like a cosmic horror novel. This galactic giant didn't grow through the relatively peaceful process of gas accretion and steady star formation that built the Milky Way. Instead, IC1101 is essentially a galactic cannibal that has spent billions of years devouring everything in its path. It sits at the center of a massive galaxy cluster, using its enormous gravitational influence to strip stars and gas from neighboring galaxies, incorporating them into its ever-growing bulk. Imagine being an astronomer in a galaxy that's about to be consumed by IC1101. You'd watch in cosmic slow motion as your galaxy's outer regions get stretched and distorted by tidal forces. Stars that had orbited your galactic center for billions of years would suddenly find themselves on escape trajectories, pulled inexorably toward the gravitational maw of the approaching giant. Entire stellar systems would be ripped from their home galaxy and cast into the vast spaces between galactic structures, becoming what astronomers call intergalactic wanderers. The central regions of IC1101 harbor secrets that make our galaxy's supermassive black hole look like a cosmic pebble. At its heart lies one of the most massive black holes ever discovered, with a mass estimated at anywhere from 40 to 100 billion times that of our Sun. This gravitational monster is so massive that its event horizon, the point of no return beyond which nothing can escape, has a diameter larger than the orbit of Neptune in our solar system. The gravitational influence of this supermassive black hole extends throughout the entire galaxy, orchestrating the motion of trillions of stars across distances that span millions of light years. The orbital velocities required to maintain stable paths around such a massive central object are mind-boggling. Stars in the outer regions of IC1101 are moving at speeds that would tear apart any smaller galactic structure, held in check only by the enormous gravitational pull of the galaxy's collective mass. But perhaps the most fascinating aspect of IC1101 is what it tells us about the future evolution of cosmic structures. This galactic giant represents the end point of galactic evolution in dense cluster environments. It's what happens when gravity is given billions of years to work its magic on a rich collection of galaxies confined to a relatively small volume of space. In essence, IC1101 is a preview of what the distant future might hold for galaxy clusters throughout the universe. The stellar populations within IC1101 are predominantly old, red stars that have been burning for billions of years. Unlike the Milky Way, which continues to form new stars at a steady rate, IC1101 has largely exhausted its supply of star-forming gas. The violent processes that built this galactic giant also heated and dispersed much of the raw material needed for continued stellar birth. What remains is a vast collection of aging suns, slowly burning through their nuclear fuel, giving the entire galaxy a distinctive reddish hue when viewed through powerful telescopes. Living in a galaxy like IC 1101 would provide a night sky experience that's completely alien to anything we can imagine from Earth. The stellar density in the central regions is so high that the night would never truly be dark. Imagine looking up and seeing not thousands of individual stars, but a continuous glow created by millions of stellar neighbors, each bright enough to cast shadows on planetary surfaces. The concept of constellations would be meaningless in such an environment, replaced by an overwhelming tapestry of light that would make navigation by stellar landmarks impossible. The gravitational environment within IC 1101 creates phenomena that simply don't exist in smaller galaxies like our own. Massive streams of stars, stripped from captured galaxies, snake through the intergalactic medium like cosmic rivers of light. These stellar streams can extend for hundreds of thousands of light years, creating temporary bridges between distant regions of the galaxy. Some of these streams are so massive that they contain more stars than entire dwarfed galaxies in our local group. The sheer scale of IC 1101 also means that communication across the galaxy would be virtually impossible for any hypothetical civilizations that might exist within it. Even traveling at the speed of light, a message sent from one edge of the galaxy to the other would take 6 million years to arrive. For comparison, 6 million years ago on Earth, our earliest human ancestors were just beginning to walk upright. The timescales involved in cross-galactic communication within IC 1101 exceed the entire evolutionary history of complex life on our planet. The discovery and study of IC 1101 has forced astronomers to revise their understanding of the upper limits of galactic mass and size. When the first measurements were made, many scientists initially rejected the results as observational errors. The idea that a single gravitationally bound structure could contain 100 trillion stars seemed to violate theoretical models of galaxy formation. How could so much matter accumulate in one location without triggering processes that would limit further growth? The answer lies in the unique environment where IC 1101 formed. This galactic giant sits at the center of the Abell 2029 galaxy cluster, one of the most massive structures in the known universe. The cluster contains thousands of galaxies, all bound together by gravity and slowly falling toward the center where IC 1101 waits like a cosmic spider in an enormous web. The cluster environment provides a continuous supply of smaller galaxies to feed the central giant, allowing it to grow far beyond the sizes possible in less dense regions of the universe. But IC 1101 isn't just passively absorbing nearby galaxies. It's actively reshaping its entire cosmic neighborhood through gravitational interactions that span hundreds of millions of light years. The galaxy's enormous mass warps the fabric of space-time itself, creating gravitational lenses that distort and magnify the images of even more distant galaxies located behind it. This gravitational lensing effect allows astronomers to study objects that would otherwise be too faint to detect, turning IC 1101 into a natural cosmic telescope. The energy requirements for maintaining such a massive structure are staggering. The gravitational binding energy of IC 1101, the amount of energy required to completely disperse all its matter into intergalactic space, exceeds the total energy output of our Sun over its entire 10 billion year lifetime by factors that require scientific notation to express. This energy is locked up in the gravitational potential well created by the galaxy's enormous mass, making it one of the most tightly bound structures in the observable universe. The existence of IC 1101 also challenges our fundamental understanding of cosmic timescales and the evolution of the universe itself. When we observe this galactic giant, we're seeing it as it existed 1 billion years ago, when the light that's now reaching our telescopes first began its journey across space. But even accounting for this cosmic time delay, the sheer size and mass of IC 1101 suggests it must have formed relatively early in the universe's history, during an epoch when galaxy formation processes were dramatically different from what we observe today. Think about it this way. The universe is only 13.8 billion years old, which means IC 1101 had to assemble its incredible mass and structure in less than 13 billion years. That might sound like plenty of time, but when you consider the complex gravitational choreography required to capture, merge, and integrate hundreds or thousands of smaller galaxies into a single coherent structure, the timeline becomes surprisingly tight. The galaxy formation models that work perfectly well for explaining the Milky Way start to break down when applied to monsters like IC 1101. This timeline problem becomes even more intriguing when we consider the rate at which IC 1101 must have been consuming other galaxies. To accumulate 100 trillion stars, this cosmic cannibal would need to devour approximately one Milky Way-sized galaxy every 100 million years throughout its entire existence. That's a feeding rate so voracious that it would quickly exhaust the supply of available prey galaxies in most cosmic neighborhoods. Only in the incredibly dense environment of a massive galaxy cluster could such sustained galactic cannibalism continue for billions of years. The stellar archaeology within IC 1101 tells a fascinating story of cosmic violence and transformation. When astronomers analyze the light spectra from different regions of the galaxy, they can identify distinct stellar populations that originated in different donor galaxies. It's like examining layers of sediment in a geological formation, except instead of rock strata, we're looking at the fossilized remains of entire galactic civilizations that were consumed eons ago. Some regions of IC 1101 contain stars with chemical compositions that match those found in spiral galaxies like our own, evidence of relatively recent galactic meals. Other areas harbor ancient stellar populations with chemical fingerprints that suggest they formed in the very early universe, when the cosmic abundance of heavy elements was much lower than it is today. These primordial stars serve as archaeological artifacts, preserving information about the conditions that existed when the first galaxies were forming. The central black hole at IC 1101's heart creates a gravitational environment so extreme that it bends the rules of physics as we understand them. With a mass potentially reaching 100 billion suns, this cosmic monster generates tidal forces that can disrupt objects at distances of several light years from its event horizon. For comparison, the tidal disruption radius around our own sun extends only a few million miles. The difference in scale is like comparing a puddle to an ocean. But here's where the physics gets really wild. The rotation period of matter in the accretion disk around IC 1101's central black hole can reach significant fractions of the speed of light. As material spirals inward toward the event horizon, it gets compressed and heated to temperatures exceeding billions of degrees, creating a cosmic furnace that outshines entire star-forming regions. The energy released by matter falling into this supermassive black hole could power the entire Milky Way for millions of years. The magnetic field environment around such a massive black hole creates phenomena that simply don't exist anywhere else in the universe. Charged particles accelerated to near light speed by the black hole's magnetic field lines generate radio emissions detectable across billions of light years. These cosmic radio beacons can persist for millions of years, creating galactic-scale structures that dwarf anything we observe in our local cosmic neighborhood. Living on a planet within IC 1101 would mean existing in a gravitational environment fundamentally different from Earth's experience. The combined gravitational pull of 100 trillion stars creates tidal effects that would be noticeable on planetary scales. Ocean tides wouldn't just respond to a single moon or star, but to the collective gravitational influence of millions of nearby stellar neighbors. The concept of a stable, circular planetary orbit would become much more complex, with gravitational perturbations from passing stars constantly nudging planetary systems into new configurations. The stellar density in IC 1101's core regions reaches levels where close encounters between stars become commonplace rather than rare events. In the Milky Way, stellar collisions are so infrequent that they might happen once every few billion years in the most crowded regions. But in the heart of IC 1101, gravitational interactions between stars occur constantly, creating a dynamic environment where planetary systems can be disrupted, stellar companions can be exchanged, and the very fabric of stellar neighborhoods undergoes continuous rearrangement. These frequent stellar interactions have profound implications for planetary formation and the potential for life. While the high stellar density might initially seem beneficial for providing energy and potentially habitable worlds, the gravitational chaos makes long-term stability extremely difficult to achieve. Planetary systems that manage to form would face constant threats from passing stars that could destabilize orbits, strip away outer planets, or even capture entire worlds, sending them wandering through interstellar space as rogue planets. The chemical evolution within IC 1101 follows patterns completely different from what we observe in the Milky Way. The massive rate of star formation in the galaxy's early history, followed by the incorporation of stellar galaxies, has populations from hundreds of consume created a complex chemical landscape where different regions have dramatically different abundances of heavy elements. Some areas might be incredibly metal-rich, containing high concentrations of elements like iron, silicon, and oxygen that are essential for rocky planet formation. Other regions could be surprisingly metal-poor, harboring ancient stellar populations that formed before the universe had time to synthesize significant quantities of heavy elements. This chemical diversity within a single galaxy creates microenvironments that could support radically different types of planetary systems. Regions rich in heavy elements might host rocky worlds similar to Earth, while metal-poor areas could contain only gas giants and icy bodies. The result would be a galactic ecosystem of incredible complexity, where the potential for life might vary dramatically depending on location within the galaxy's vast structure. The energy budget of IC 1101 operates on scales that challenge human comprehension. The total luminosity of this galactic giant, the combined light output from 100 trillion stars, exceeds the energy production of the Milky Way by a factor of several hundred. If we could somehow capture and harness just 1% of IC 1101's total energy output, it would be sufficient to power human civilization at current consumption levels for longer than the universe has existed. But the most mind-bending aspect of IC 1101 isn't its current state, it's what this galactic monster represents for the future evolution of cosmic structure. Current models of cosmological evolution suggest that as the universe continues to expand and age, galaxy clusters like the one containing IC 1101 will become increasingly isolated from their neighbors. Dark energy will drive distant galaxy clusters beyond the cosmic horizon, making them forever unreachable and invisible. Within these isolated island universes, gravity will continue its relentless work, causing galaxies to merge and coalesce into ever larger structures. Eventually, billions of years in the future, each galaxy cluster will collapse into a single, unimaginably massive galaxy that makes even IC 1101 look small by comparison. These future cosmic giants might contain quadrillions of stars and span tens of millions of light years, representing the final stage of gravitational structure formation in our universe. The study of IC 1101 therefore provides us with a glimpse into humanity's cosmic future, a preview of the universe that will exist long after our sun has died and our galaxy has been transformed beyond recognition. In this distant future, the night sky will look completely different, dominated by a single enormous galaxy containing virtually all the matter in what was once a rich cluster of thousands of separate galactic islands. The gravitational dynamics within IC 1101 create stellar velocities that would tear apart smaller galactic structures. Stars in the outermost regions of this cosmic behemoth are moving at speeds exceeding 2,000 kilometers per second relative to the galactic center. To put that in perspective, that's fast enough to travel from New York to Los Angeles in less than 2 seconds. These extreme velocities are necessary to maintain stable orbits around the galaxy's enormous gravitational well, but they also create an environment where stellar interactions occur on completely different timescales than anything we observe in the Milky Way. The thermal environment within IC 1101 tells another fascinating story about galactic evolution. When galaxies collide and merge, the process generates enormous amounts of heat through gravitational compression and shock waves propagating through interstellar gas. This thermal energy can reach temperatures of millions of degrees, hot enough to strip electrons from atoms and create vast regions of ionized plasma that glow with X-ray radiation. The accumulated thermal history of IC 1101, built up through billions of years of galactic cannibalism, has created a hot gas halo that extends far beyond the visible boundaries of the galaxy itself. This superheated gas envelope serves as a fossil record of every major merger event in the galaxy's history. Different temperature regions correspond to different epochs of galactic consumption, creating a three-dimensional thermal map that astronomers can use to reconstruct the galaxy's violent past. It's like reading the rings of an ancient tree, except instead of annual growth patterns, we're examining the thermal signatures of cosmic collisions that occurred billions of years ago. The dark matter structure underlying IC 1101 represents one of the most massive gravitational concentrations in the known universe. While we can't directly observe dark matter, its presence is revealed through gravitational lensing effects and the orbital dynamics of stars within the galaxy. Computer simulations suggest that IC 1101 sits at the center of a dark matter halo containing the equivalent mass of 10 trillion suns, creating a gravitational potential well so deep that it can capture and retain matter from distances exceeding 1,000,000 light-years. This dark matter scaffolding extends far beyond the visible galaxy, creating what astronomers call a galactic sphere of influence. Any smaller galaxy that wanders within this invisible boundary becomes gravitationally bound to IC 1101, doomed to eventual consumption regardless of its initial trajectory or velocity. The sphere of influence for IC 1101 is so large that it encompasses volumes of space containing hundreds of smaller galaxies, all slowly spiraling inward toward their ultimate fate as stellar fuel for the central giant. The process of galactic digestion within IC 1101 follows predictable patterns that astronomers have learned to identify through detailed observations. When a smaller galaxy first approaches the giant's gravitational boundary, it begins to experience tidal distortion as different parts of the galaxy feel slightly different gravitational forces. The outer regions, being farther from the galaxy's center, experience weaker self-gravity and are the first to be stripped away by IC 1101's tidal forces. These stripped stars don't immediately join the main body of IC 1101. Instead, they form extended stellar streams that can persist for hundreds of millions of years, creating temporary structures that snake through the space between galaxies like cosmic ribbons of light. Some of these tidal streams extend for distances greater than the diameter of our entire local group, creating bridge-like connections between IC 1101 and its most recent victims. The stellar archaeology preserved in these tidal streams provides invaluable information about the types of galaxies that IC 1101 has consumed throughout its history. By analyzing the chemical compositions, ages, and orbital characteristics of stars within different streams, astronomers can essentially perform cosmic forensics, reconstructing the properties of galaxies that were destroyed billions of years ago. It's like examining the stomach contents of a cosmic predator to understand the ecosystem it inhabits. But IC 1101's influence extends beyond simple galactic cannibalism. The galaxy's enormous mass creates gravitational effects that influence star formation rates in nearby galaxies long before they're actually consumed. Smaller galaxies approaching the giant experience gravitational compression that can trigger intense bursts of star formation, causing them to burn through their gas reserves much faster than they would in isolation. This process, called starvation, gradually transforms spiral galaxies into gas-poor ellipticals before they're eventually absorbed into IC 1101's structure. The magnetic field environment around IC 1101 operates on scales that dwarf anything we observe in the Milky Way. The galaxy's central supermassive black hole generates magnetic field lines that extend throughout the entire galactic structure, creating a unified electromagnetic environment spanning millions of light-years. These magnetic fields channel high-energy particles ejected from the central black hole, creating radio lobes that can extend far beyond the galaxy's visible boundaries. The interaction between IC 1101's magnetic field and the surrounding intergalactic medium creates phenomena that serve as cosmic laboratories for studying physics under extreme conditions. Shock fronts propagating through the magnetized plasma can accelerate particles to energies that exceed anything achievable in terrestrial particle accelerators. These cosmic ray particles, traveling at nearly the speed of light, carry information about the physical processes occurring in IC 1101's core across vast distances, allowing astronomers to study the galaxy's central engine through indirect observations. The time dilation effects within IC 1101's gravitational field create another layer of complexity for understanding this cosmic giant. According to Einstein's theory of general relativity, time passes more slowly in strong gravitational fields. While this effect is negligible for most astronomical objects, the extreme mass concentration in IC 1101's core creates measurable time dilation that affects everything from stellar evolution rates to the frequency of light emitted by atoms in the galaxy's central regions. For hypothetical observers located in different parts of IC 1101, time itself would flow at slightly different rates. An observer near the galactic center would age more slowly relative to someone in the outer regions, creating a gradient of temporal flow across the galaxy's structure. Over billions of years, these relativistic effects accumulate to create measurable differences in stellar ages and evolutionary states between different regions of the galaxy. The neutrino environment within IC 1101 represents another extreme that has no parallel in our galactic neighborhood. With 100 trillion stars undergoing nuclear fusion, the galaxy produces neutrinos at a rate that exceeds the Milky Way's output by factors of thousands. These ghostly particles, which barely interact with matter, stream outward from stellar cores throughout the galaxy, creating a neutrino background radiation that would be detectable from enormous distances. The cumulative neutrino flux from IC 1101 is so intense that it could theoretically be detected by sensitive instruments located in neighboring galaxy clusters. This neutrino signature serves as a direct probe of the nuclear processes occurring in the galaxy's stellar population, providing information about star formation rates, stellar masses, and the overall health of the galactic ecosystem that can't be obtained through traditional optical observations. The gravitational wave environment around IC 1101 creates another unique signature of this cosmic giant. With such an enormous population of stellar remnants, including neutron stars and black holes, the galaxy hosts countless compact object mergers that generate ripples in space-time. The rate of neutron star mergers alone within IC 1101 exceeds the rate for the entire observable universe by several orders of magnitude, creating a continuous background of gravitational waves that could be detected by future space-based observatories. These gravitational wave signals carry information about the galaxy's stellar evolution history encoded in the frequencies and amplitudes of space-time ripples. Different types of compact object mergers produce characteristic gravitational wave signatures, allowing astronomers to use these signals as cosmic seismographs for studying the internal structure and dynamics of distant galaxies. The chemical enrichment history of IC 1101 reveals patterns that challenge our understanding of stellar nucleosynthesis and galactic chemical evolution. The galaxy's massive stellar population has produced and dispersed heavy elements at rates that far exceed anything observed in smaller galaxies. The cumulative effect of 100 trillion stars living and dying over billions of years has created regions within IC 1101 where the abundance of elements like iron, silicon, and oxygen exceeds solar values by factors of 10 or more. This extreme chemical enrichment creates environments where planet formation processes might follow completely different pathways than what we observe in our solar system. Rocky planets forming in these metal-rich regions could have compositions dominated by heavy elements, potentially creating worlds with exotic mineralogy and geological processes that have no terrestrial analogues. The high metal content might also affect atmospheric evolution, creating dense, heavy atmospheres that could trap heat more efficiently or support different types of atmospheric chemistry. The stellar mass function within IC 1101 shows interesting deviations from what astronomers observe in typical galaxies. The process of repeated galactic mergers has preferentially preserved the most massive stars from consumed galaxies while stripping away lower mass stellar populations. This mass segregation effect has created regions within IC 1101 that are dominated by stellar remnants like white dwarfs, neutron stars, and stellar mass black holes, creating gravitational environments unlike anything in the Milky Way. The density of compact objects in IC 1101's core regions reaches levels where gravitational wave interactions become commonplace. Binary black hole systems, which are rare in normal galaxies, form frequently through dynamical interactions in the crowded stellar environment. These systems eventually merge, producing gravitational wave bursts that could be detected across cosmological distances, making IC 11011 one of the loudest sources of space-time ripples in the local universe. The photon environment within IC 1101 creates radiation conditions that would be lethal to any Earth-like life forms. The combined stellar radiation from 100 trillion stars, enhanced by reflection and scattering from interstellar dust, creates background radiation levels thousands of times higher than what we experience in our solar neighborhood. This intense radiation field affects everything from planetary atmospheric evolution to the survival of organic molecules in interstellar space. The infrared emission from IC 1101 tells another story about the galaxy's thermal history and dust content. The enormous stellar population has produced vast quantities of heavy elements that condense into dust grains in the cool outer atmospheres of aging stars. This dust absorbs visible and ultraviolet radiation from stellar surfaces and re-emits the energy at infrared wavelengths, creating a thermal glow that can be detected across billions of light years. The dust distribution within IC 1101 follows patterns that reflect the galaxy's merger history. Different dust compositions correspond to different stellar populations, creating a three-dimensional map of the galaxy's chemical evolution. Regions rich in silicate dust indicate areas where massive stars have recently exploded as supernovae, while carbon-rich dust signatures point to regions dominated by intermediate mass stars in their final evolutionary phases. The cosmic ray environment within IC 1101 reaches energy densities that would sterilize planetary surfaces across vast regions of the galaxy. The combination of supernova explosions, black hole activity, and stellar collisions creates a particle accelerator on galactic scales, producing cosmic rays with energies that exceed anything observed in our local cosmic neighborhood. These high-energy particles propagate throughout the galaxy's magnetic, creating a per-field structure-evasive radiation environment that would pose significant challenges for the development and survival of life. The study of IC 1101 has also revealed important insights about the maximum possible size of gravitationally bound structures in the universe. Current cosmological models suggest that their mechanisms begin to limit further our fundamental limits to how large galaxies can grow before various feedback mass accumulation. IC 1101 appears to be approaching these theoretical limits, representing what might be the maximum possible size for a single galaxy in our universe. The existence of IC 1101 near these theoretical limits raises fascinating questions about the role of dark energy in shaping cosmic structure formation. As the universe continues to expand and dark energy becomes increasingly dominant, the conditions that allowed IC 1101 to form may never occur again. This galactic giant might represent a unique product of a specific epoch in cosmic history, when the balance between gravitational attraction and cosmic expansion allowed for the formation of structures that will never be replicated in the future evolution of our universe. The observational challenges posed by studying IC 1101 have pushed astronomical technology to its limits and beyond. The galaxy's enormous angular size on the sky means that capturing complete images requires telescope surveys spanning multiple years of observation time. Even with the most powerful instruments available, astronomers can only study the galaxy's global properties while missing the detailed structure that would be visible in smaller, nearby galaxies. Future space-based telescopes and interferometric arrays will eventually provide the resolution needed to study individual stellar populations within IC 1101, but the data analysis challenges will be enormous. Processing observations of 100 trillion stars requires computational resources that exceed current capabilities by orders of magnitude. The complete characterization of IC 1101's stellar content would generate datasets larger than all current astronomical archives combined, pushing the boundaries of both observational technology and data analysis techniques. The computational challenges of modeling IC 1101's gravitational dynamics require supercomputers that can simulate the interactions between trillions of individual objects over billions of years of cosmic time. Current galaxy simulation codes begin to break down when applied to structures this massive, not because the physics is wrong, but because the sheer number of calculations required exceeds the processing power of even the world's most advanced computing facilities. To put this in perspective, simulating just 1 million years of IC1101's evolution with full gravitational accuracy would require computational time measured in centuries using today's technology. The problem scales exponentially with the number of particles being tracked, meaning that truly comprehensive simulations of this galactic giant may remain beyond our reach until quantum computing or other revolutionary technologies become available. The observational legacy of IC1101 extends far beyond its own impressive statistics. This cosmic behemoth serves as a gravitational telescope, using its enormous mass to bend and focus light from even more distant objects located behind it. The gravitational lensing effects created by IC1101 have allowed astronomers to study galaxies that formed when the universe was less than 1 billion years old, providing crucial insights into the earliest epochs of cosmic structure formation. These lensed background galaxies appear as distorted arcs and multiple images around IC1101's periphery, creating a natural laboratory for studying galaxy evolution across cosmic time. Some of the most distant galaxies ever observed have been discovered through IC1101's gravitational lens, objects so far away that their light has been traveling toward us for over 12 billion years. Without the magnifying power of IC1101's gravity, these ancient galaxies would remain forever invisible to our current generation of telescopes. The stellar life cycle within IC1101 operates under conditions that have no equivalent in our galactic neighborhood. The high stellar density and frequent gravitational interactions create environments where stellar evolution proceeds along pathways that rarely occur in isolation. Binary star systems form through chance encounters rather than during initial star formation, leading to exotic stellar configurations that can't be reproduced in stellar evolution models developed for normal galactic environments. The rate of stellar collisions within IC1101's core reaches levels where direct physical contact between stars becomes a significant evolutionary pathway. When two main sequence stars collide at the velocities typical in IC1101's central regions, the result isn't destruction, but rather the formation of blue straggler stars that appear younger and more massive than the surrounding stellar population. These collision products can live for hundreds of millions of years longer than normal stars of equivalent mass, creating stellar populations that seem to violate the usual rules of stellar aging. The exotic stellar evolution pathways within IC1101 also produce unusual types of stellar remnants. The high-pressure environment created by the galaxy's intense gravitational field can affect the final stages of stellar collapse, potentially creating neutron stars with properties that differ significantly from those formed in lower-density environments. Some theoretical models suggest that the extreme conditions within IC1101 might even allow for the formation of hypothetical quark stars, exotic objects where nuclear matter breaks down into its fundamental constituents. The planetary system dynamics within IC1101 would be unlike anything we can observe in our cosmic neighborhood. The gravitational environment is so complex that the concept of stable planetary orbits becomes meaningless for all but the most tightly bound systems. Planets would experience constant gravitational perturbations from passing stars, leading to orbital evolution timescales measured in millions rather than billions of years. This gravitational chaos would create a population of rogue planets vastly exceeding anything we observe in the Milky Way. Computer simulations suggest that IC1101 might contain more free-floating planets than gravitationally bound ones, with trillions of worlds wandering through interstellar space after being ejected from their birth systems by gravitational encounters. These orphaned worlds would experience temperature variations as they drift between different stellar neighborhoods, potentially creating unique evolutionary environments for any life-extreme conditions. The magnetic field structure forms hardy enough to survive such within IC1101 creates phenomena that operate on scales comparable to the galaxy's overall dimensions. The central supermassive black hole generates magnetic field lines that thread through the entire galactic structure, creating a unified electromagnetic environment that can channel energy and particles across millions of light years. This galactic-scale magnetic field serves as a cosmic particle accelerator, creating high-energy phenomena that dwarf anything observed in smaller galaxies. The interaction between IC1101's magnetic field and the surrounding intergalactic medium generates radio emissions detectable across billions of light-years. These radio signals carry encoded information about the galaxy's internal structure and dynamics, allowing astronomers to study processes occurring in the galactic core through observations of electromagnetic radiation that escapes the system. The radio signature of IC1101 is so distinctive that it could be identified and studied even if the galaxy were located at the edge of the observable universe. The chemical evolution within IC1101 has created regions where the abundance of heavy elements exceeds anything observed in normal galactic environments. The cumulative effect of stellar nucleosynthesis in 100 trillion stars has produced chemical compositions that approach theoretical limits for stellar metal enrichment. Some regions within the galaxy contain gas clouds where elements like iron and silicon are more abundant than hydrogen, creating conditions that would fundamentally alter the physics of star formation and planetary system development. These chemically extreme environments within IC1101 serve as natural laboratories for studying nucleosynthesis processes under conditions that can't be replicated elsewhere in the observable universe. The high metal abundances affect everything from the opacity of stellar atmospheres to the types of molecules that can form in interstellar space, creating astrophysical environments that require entirely new theoretical frameworks to understand properly. The energy budget of IC1101 operates on scales that challenge our understanding of cosmic energy transport and dissipation. The galaxy's total energy output, combining stellar radiation, black hole emissions, and gravitational potential energy, approaches levels where relativistic effects become important for understanding the system's overall energetics. The binding energy required to hold 100 trillion stars in gravitational equilibrium represents one of the largest concentrations of potential energy in the observable universe. The thermal evolution of IC1101 tells a story of cosmic violence spanning billions of years. Each galactic merger that contributed to the giant's growth deposited enormous amounts of heat into the surrounding gas, creating temperature distributions that persist for cosmological timescales. The accumulated thermal history of the galaxy creates a complex three-dimensional temperature map that serves as a fossil record of every major accretion event in its violent past. The study of IC1101 has revealed fundamental insights about the relationship between galaxy mass and central black hole mass that extend far beyond what can be learned from smaller systems. The galaxy's central black hole, with its mass of potentially 100 billion suns, represents the extreme end of the black hole mass distribution in the universe. Understanding how such massive black holes form and evolve requires theoretical models that push beyond the limits of current astrophysical understanding. The accretion processes around IC1101's central black hole operate in regimes where general relativistic effects become dominant over Newtonian gravity. The inner regions of the accretion disk experience time dilation effects so severe that the rate of physical processes becomes dramatically different from what would be observed in weaker gravitational fields. These relativistic effects create observational signatures that can be detected through careful spectroscopic analysis of the galaxy's core emission. The influence of IC1101 extends far beyond its visible boundaries through gravitational effects that shape the evolution of its entire galaxy cluster. The giant's enormous mass creates tidal forces that can strip gas from galaxies located millions of light-years away, preventing star formation in satellite systems long before they're actually absorbed into the central galaxy. This process of environmental quenching has transformed the entire cluster into a region dominated by gas-poor, star formation inactive galaxies. The future evolution of IC1101 will be shaped by the ongoing expansion of the universe and the increasing dominance of dark energy over gravitational attraction. As cosmic expansion accelerates, the galaxy will become increasingly isolated from external sources of fuel, eventually exhausting its ability to grow through continued mergers and accretion. The end state of this process will be a slowly aging giant, gradually fading as its stellar population evolves toward lower mass, longer-lived stars. The stellar population synthesis within IC1101 creates spectral signatures that serve as templates for understanding galaxy evolution across cosmic time. The galaxy's integrated spectrum contains contributions from stellar populations spanning the entire history of star formation in the universe, creating a library of stellar evolution effects that can be used to interpret observations of distant galaxies observed at earlier cosmic epochs. The dust production within IC1101 operates at rates that exceed the combined output of thousands of normal galaxies. The enormous population of evolved stars continuously enriches the interstellar medium with heavy elements that condense into dust grains, creating a self-reinforcing cycle where dust production enables further star formation, which in turn produces more dust-forming stars. This feedback loop has created dust masses within IC1101 that approach theoretical limits for gravitational stability. The cosmic ray acceleration within IC1101 creates particle energies that exceed anything achievable in terrestrial laboratories by orders of magnitude. The galaxy serves as a natural particle accelerator on scales that dwarf human technology, producing cosmic rays with energies approaching the theoretical cutoff limits imposed by interactions with cosmic microwave background radiation. These ultra-high energy particles carry information about the most extreme physical processes occurring within the galaxy across intergalactic distances. The neutrino production within IC1101 creates a detectable signature that could theoretically be observed from neighboring galaxy clusters using sufficiently sensitive detectors. The cumulative neutrino flux from 100 trillion stars undergoing nuclear fusion produces a characteristic energy spectrum that encodes information about the galaxy's stellar mass function and evolutionary state. Future neutrino observatories might be able to use IC1101 as a standard candle for calibrating neutrino astronomy techniques. The gravitational wave environment around IC1101 creates a rich tapestry of space-time disturbances from countless compact object mergers occurring throughout the galaxy's volume. The merger rate of neutron star and black hole binaries within this system exceeds the rate for entire normal galaxies by factors of thousands, creating a continuous background of gravitational wave signals that future space-based detectors should be able to resolve and study in detail. The observational challenges posed by IC1101 continue to drive technological development in astronomical instrumentation. The galaxy's enormous angular size and complex internal structure require observation strategies that combine multiple telescopes and observation techniques to build up complete pictures of its properties. Even with next-generation space telescopes, fully characterizing this galactic giant will require decades of dedicated observation time and analysis effort. The theoretical implications of IC1101's existence extend to fundamental questions about the nature of cosmic structure formation and the role of dark matter in shaping the universe's largest gravitationally bound objects. The galaxy represents a natural experiment in extreme gravitational physics, providing observational tests of theoretical models that operate at the intersection of cosmology, stellar astrophysics, and general relativity. The legacy of IC1101 in astronomical research will extend far beyond its own intrinsic properties. This cosmic giant serves as a benchmark against which all other galaxies are measured, defining the upper limit of what's possible for gravitationally bound stellar systems in our universe. Its study has revealed new classes of astrophysical phenomena and pushed theoretical models to their limits, creating a foundation for understanding galaxy evolution that will influence astronomical research for generations to come. The sheer scale of IC1101 forces us to confront the limitations of human intuition when dealing with cosmic phenomena. The numbers involved in describing this galactic giant strain our ability to comprehend scale and magnitude, requiring new ways of thinking about space, time, and the organization of matter in the universe. Yet this challenge to our understanding is precisely what makes IC1101 so scientifically valuable, pushing us to expand our conceptual frameworks and develop new tools for exploring the cosmos. As we stand in our backyards looking up at the Milky Way's gentle glow across the night sky, it's worth remembering that somewhere in the vast darkness beyond our vision lies a cosmic giant that makes our entire galactic home look like a single star in comparison. IC1101 represents the universe at its most extreme, a reminder that cosmic evolution can produce structures so massive and complex that they challenge our deepest understanding of how the universe actually works. The comparison between our cosmic neighborhood and this galactic behemoth reveals just how diverse and remarkable the universe truly is. From our perspective as inhabitants of a relatively modest spiral galaxy, IC1101 seems almost incomprehensibly massive and alien. Yet both galaxies operate according to the same fundamental physical laws, shaped by gravity, stellar evolution, and the slow dance of cosmic time that governs all structure in the observable universe. But perhaps the most profound implication of IC 1101's existence isn't what it tells us about that distant galactic giant, but what it reveals about the fundamental nature of cosmic evolution itself. When we study this monster galaxy, we're essentially looking at a preview of our own galactic future, because the universe doesn't create structures like IC 1101 in isolation. They endpoint represent the inevitable of gravitational evolution in the richest, most dense regions of the cosmos. Think about it this way. Right now, as you're watching this video, the Milky Way is already on a collision course with several smaller galaxies. The Magellanic Clouds, those satellite galaxies I mentioned earlier, are slowly spiraling inward and will eventually be absorbed into our galactic structure. In about 4.5 billion years, we're going to collide with the Andromeda Galaxy, creating a new elliptical galaxy that astronomers have already nicknamed Milky Way. And that's just the beginning. Our local group of galaxies exists within a larger structure called the Virgo supercluster, which itself is part of an even more massive structure known as Laniakea. All of these cosmic neighborhoods are slowly falling toward gravitational attractors, regions where dark matter has accumulated in such enormous quantities that they're pulling in everything around them across hundreds of millions of light years. The process that created IC 1101 is happening everywhere in the universe, just at different stages and different scales. Galaxy clusters are continuously growing, merging and evolving into ever larger structures. What we're witnessing when we observe IC 1101 isn't just an isolated cosmic phenomenon, it's a glimpse into the far future of galaxy evolution throughout the observable universe. But here's where things get really mind-bending. The expansion of the universe, driven by dark energy, is actually working against this process of gravitational consolidation. While gravity tries to pull galaxies together into larger and larger structures, the accelerating expansion of space itself is driving distant galaxy clusters apart faster than they can gravitationally attract each other. This creates a cosmic race between gravity and expansion, and the outcome determines the ultimate fate of structure formation in our universe. In regions where gravity wins, we get monsters like IC 1101 that continue growing by consuming everything in their gravitational reach. But in regions where dark energy dominates, galaxy clusters become isolated island universes, forever separated from their neighbors by the relentless expansion of space. Current cosmological models suggest that we're living through a unique epoch in cosmic history when both processes are operating simultaneously. In the distant future, perhaps 100 billion years from now, the universe will look completely different. Dark energy will have driven most galaxy clusters beyond each other's cosmic horizons, creating isolated pockets of matter scattered throughout an otherwise empty and expanding void. Within each of these isolated regions, gravity will continue its work unopposed, causing all the galaxies to eventually merge into single, massive elliptical systems that make even IC 1101 look modest by comparison. These future cosmic giants might contain quadrillions of stars and span tens of millions of light years, representing the absolute final stage of gravitational structure formation. But there's an even more disturbing implication hidden in this cosmic evolution story. The process that creates galactic giants like IC 1101 is fundamentally destructive to the conditions that allow for complex structure formation on smaller scales. When galaxies merge and consolidate into these massive elliptical systems, they consume and destroy the very environments where new stars are born, and planetary systems can form and evolve in relative stability. The regions within IC 1101 where stellar density is highest are also the regions where planetary systems would be least likely to survive long enough for complex chemistry to develop. The gravitational chaos, high radiation levels, and frequent stellar encounters create an environment that's actively hostile to the long-term conditions that seem to be necessary for the emergence of complex life. This raises a profound question about the relationship between cosmic evolution and biological evolution. As the universe ages and galaxies grow larger through mergers and accretion, are we simultaneously destroying the cosmic environments that are most conducive to the development of life and intelligence? Could it be that we're living through a brief window in cosmic history when the universe is organized in just the right way to support the emergence of complex structures like living organisms and technological civilizations? The answer to this question has implications that extend far beyond astronomy and cosmology. If large-scale cosmic evolution is indeed working against the conditions necessary for life, then the emergence of intelligence anywhere in the universe represents an incredibly rare and precious phenomenon that becomes increasingly unlikely as cosmic time progresses. From this perspective, the existence of IC1101 isn't just a fascinating example of extreme cosmic engineering. It's a reminder that the universe is constantly changing in ways that might make the emergence of life and intelligence increasingly difficult over time. The cosmic conditions that allowed our solar system to form in a stable galactic environment might represent a temporary phase that will eventually be eliminated by the relentless process of gravitational consolidation. But there's another way to interpret this cosmic story, one that's more optimistic about the long-term prospects for life and intelligence in the universe. While it's true that the cores of giant elliptical galaxies like IC1101 represent hostile environments for planetary system formation, the outer regions of these cosmic giants might actually provide more stable and long-lived environments than anything available in smaller galaxies. The gravitational stability provided by IC1101's enormous mass means that stars in the galaxy's outer regions can maintain stable orbits for incredibly long periods of time. Unlike the Milky Way, where spiral density waves and gravitational interactions with satellite galaxies create ongoing disturbances, the outer reaches of IC1101 represent some of the most gravitationally stable environments in the entire universe. Stars in these regions could potentially maintain stable for timescales that exceed planetary systems the current age of the universe by factors of 10 or more. If life can somehow emerge and survive in these environments, it would have access to energy sources and stable conditions that could persist for hundreds of billions of years, far longer than anything possible in more dynamic galactic environments. The chemical environment in IC1101's outer regions also provides advantages that don't exist in smaller galaxies. The enormous rate of stellar nucleosynthesis throughout the galaxy's history has enriched even the most distant regions with heavy elements to levels that exceed anything available in the early universe. This chemical enrichment could provide the raw materials necessary for the formation of complex rocky planets and the organic chemistry that seems to be essential for the emergence of life. From this perspective, galaxies like IC1101 might not represent the end of cosmic habitability, but rather its ultimate expression. The stable, chemically enriched environments in their outer regions could serve as cosmic nurseries where life and intelligence have access to resources and timescales that dwarf anything available in younger, smaller galactic systems. The implications of this possibility are staggering to contemplate. If civilizations can emerge and survive in the outer regions of giant elliptical galaxies, they would have access to energy sources that could power technological development for timescales that exceed human comprehension. With hundreds of billions of years of stable stellar energy available, such civilizations could potentially achieve levels of technological sophistication that make our current capabilities look primitive by comparison. They might develop the ability to harness the energy output of entire stellar populations, manipulate matter and energy on galactic scales, or even engineer cosmic structures according to their needs and preferences. The timescales available for such development are so vast that virtually any technological capability that doesn't violate fundamental physical laws might eventually be achievable. But this leads to an even more profound question about our cosmic situation. If giant elliptical galaxies like IC1101 represent optimal environments for the long-term development of intelligence and technology, and if such galaxies are the inevitable result of cosmic evolution, then why don't we observe obvious signs of advanced civilizations throughout the universe? This question touches on one of the deepest mysteries in all of science, the so-called Fermi paradox. Given the vast number of stars and potentially habitable planets in the observable universe, and the enormous timescales available for the development of intelligence and technology, we might expect to see clear evidence of advanced civilizations almost everywhere we look. Yet despite decades of searching with increasingly sophisticated instruments, we've found no convincing evidence of technological intelligence beyond Earth. The existence of galaxies like IC1101 makes this paradox even more puzzling. If these cosmic giants provide optimal conditions for the long-term development of advanced civilizations, then they should be the most likely places to find evidence of cosmic engineering, stellar manipulation, or other signatures of technological intelligence operating on astronomical scales. The fact that we don't observe such signatures in IC1101 or other giant elliptical galaxies suggests either that advanced civilizations are far rarer than we might expect, or that they operate according to principles that make their activities undetectable from our current observational perspective. Neither possibility is particularly comforting for those who hope to find evidence of cosmic companionship in the universe. The study of IC1101 therefore forces us to confront some of the most fundamental questions about our place in the cosmic order. Are we alone in a universe full of magnificent but lifeless structures? Are we living through a brief moment of cosmic history when conditions are optimal for the emergence of intelligence, before gravitational evolution destroys the environments that make such emergence possible? Or are we simply too primitive and short-lived to recognize the activities of civilizations that operate on time and space scales that exceed our comprehension? These questions don't have easy answers, but they highlight the profound importance of continuing to study extreme cosmic structures like IC1101. Every new observation and theoretical insight brings us closer to understanding the fundamental principles that govern cosmic evolution and the emergence of complexity in the universe. The technological challenges of studying IC1101 in detail continue to push the boundaries of what's possible with current astronomical instrumentation. The galaxy's enormous distance and complex internal structure require observation strategies that combine data from multiple wavelengths, multiple telescopes, and multiple observation epochs to build up complete pictures of its properties and behavior. Future space-based telescopes, including the next generation of infrared observatories and gravitational wave detectors, will provide new windows into IC1101's internal structure and dynamics. These instruments will allow astronomers to study individual stellar populations within the galaxy, map the distribution of dark matter throughout its structure, and potentially detect the gravitational wave signatures of compact object mergers occurring within its bounds. The computational challenges of modeling IC1101's evolution and internal dynamics are equally formidable. Current galaxy simulation codes require massive supercomputing resources to model even relatively simple galactic systems over cosmological timescales. Simulating a structure as complex as IC1101, with its 100 trillion stars and complicated merger history, pushes beyond the limits of current computational capabilities. But these technological challenges also drive innovation in ways that benefit astronomy as a whole. The techniques developed for studying extreme systems like IC1101 often find applications in research on more typical galactic environments, advancing our understanding of galaxy formation and evolution across the entire observable universe. The observational legacy of IC1101 extends far beyond its own intrinsic properties through its role as a gravitational lens for studying even more distant cosmic structures. The galaxy's enormous mass creates lensing effects that magnify and distort the images of background galaxies, allowing astronomers to study objects that would otherwise be too faint to detect with current technology. Some of the most distant galaxies ever observed have been discovered through IC1101's gravitational lens, objects so far away that their light has been traveling toward us for over 12 billion years. These lensed galaxies provide crucial insights into the early stages of cosmic structure formation, when the universe was less than 10% of its current age and the first generation of galaxies was just beginning to form. The study of these gravitationally lensed background galaxies has revealed that galaxy formation in the early universe followed patterns that were significantly different from what we observe in the local cosmic environment. The high redshift galaxies visible through IC1101's lens show evidence of more intense star formation, different chemical compositions, and more compact structures than their present-day counterparts. This observational evidence for cosmic evolution in galaxy properties provides crucial tests of theoretical models for how cosmic structures form and evolve over time. The data obtained through IC1101's natural telescope helps astronomers refine their understanding of the physical processes that drive galaxy formation across the entire history of the universe. The multi-wavelength observations of IC1101 reveal different aspects of the galaxy's structure and composition that aren't visible in optical light alone. Radio observations detect synchrotron emission from relativistic particles, accelerated by the galaxy's central black hole and distributed magnetic fields. X-ray observations reveal hot gas heated by gravitational compression during galactic mergers. Infrared observations penetrate dust obscuration to study stellar populations and star formation activity throughout the galaxy's wavelength regime structure. Each provides unique insights into different physical processes operating within the galaxy, but combining all these observations into a coherent picture of IC1101's overall properties requires sophisticated analysis techniques and theoretical modeling frameworks. The multi-wavelength approach to studying this cosmic giant has become a template for investigating other extreme galactic systems throughout the observable universe. The chemical abundance patterns within IC1101 provide a fossil record of stellar nucleosynthesis processes operating over billions of years of cosmic time. Different elements are produced by different types of stellar explosions and evolutionary processes, so the abundance ratios observed in various regions of the galaxy encode information about the star formation history and merger events that shaped its evolution. The extreme chemical enrichment observed in some regions of IC1101 approaches theoretical limits for stellar nucleosynthesis efficiency. These chemically enhanced environments provide natural laboratories for studying nucleosynthesis processes under conditions that can't be replicated in smaller galactic systems or laboratory experiments. The dust production and destruction cycles within IC1101 operate at rates that exceed anything observed in normal galactic environments. The enormous stellar population continuously produces heavy elements that condense into dust grains, while shock waves from supernova explosions and galactic mergers destroy existing dust and redistribute it throughout the galaxy's structure. This balance between dust production and destruction creates complex spatial patterns in the galaxy's infrared emission that encode information about its star formation history and internal dynamics. The study of these dust distribution patterns provides insights into the physical processes that regulate star formation and chemical evolution in extreme galactic environments. The magnetic field structure within IC1101 represents one of the largest organized electromagnetic phenomena in the observable universe. The galaxy's central supermassive black hole generates magnetic field lines that thread through the entire galactic structure, creating a unified electromagnetic environment that can channel energy and particles across millions of light years. The interaction between this galactic-scale magnetic field and the surrounding intergalactic medium creates radio emission that can be detected across cosmological distances. These radio signals carry encoded information about the galaxy's internal structure and central black hole activity, providing a remote sensing technique for studying processes that occur deep within the galaxy's core. The temporal dynamics within IC1101 create phenomena that operate on timescales beyond human comprehension. While processes in our galaxy unfold over millions or billions of years, the sheer scale of this cosmic giant means that structural changes occur over periods that exceed the current age of the universe. Stellar streams created by tidal disruption of smaller galaxies can persist for tens of billions of years, slowly dissipating as gravitational interactions gradually randomize their orbits. The gravitational memory embedded within IC1101's structure preserves information about merger events that occurred when the universe was young. Like cosmic archaeology, astronomers can read the galaxy's current configuration to reconstruct collision sequences that happened billions of years ago. Each absorbed galaxy leaves its signature in the orbital distribution of stars, creating layered patterns that tell the story of cosmic violence spanning eons. But here's where the physics becomes truly mind-bending. The gravitational potential well created by IC1101 is so deep that it affects the rate at which time itself passes. According to Einstein's theory of general relativity, massive objects slow down the flow of time in their immediate vicinity. While this effect is negligible for most astronomical objects, the extreme mass concentration in IC1101 creates measurable time dilation effects throughout its structure. An observer located in the galaxy's central regions would experience time passing slightly more slowly relative to someone positioned in the outer halo. Over billions of years, these relativistic effects accumulate to create measurable differences in stellar evolution rates between different regions of the galaxy. Stars near the center age more slowly than their counterparts in the outer regions, creating age gradients that can be detected through spectroscopic analysis. The energy dissipation mechanisms within IC 1101 operate on scales that dwarf anything we observe in smaller galaxies. When smaller galaxies are torn apart by tidal forces, the gravitational energy released during the disruption process gets converted into heat, kinetic energy of stellar motions, and electromagnetic radiation. The cumulative effect of hundreds of such disruption events has created an energy budget that approaches the binding energy of the galaxy itself. This energy dissipation creates a thermal history that's permanently encoded in the galaxy's current structure. Different regions show temperature signatures corresponding to different epochs of violent merger activity. The hottest regions mark locations where major galactic collisions occurred relatively recently, while cooler areas indicate zones that have remained relatively undisturbed for billions of years. The stellar IC 1101 reaches velocity dispersion within levels that would tear apart any smaller galactic structure. Stars in the galaxy's core regions move at speeds exceeding 1,000 kilometers per second relative to the galactic center, velocities so high that they approach the escape velocity needed to leave the galaxy entirely. Only the enormous gravitational pull of the galaxy's collective mass keeps these high-velocity stars gravitationally bound to the system. These extreme stellar velocities create a kinetic energy reservoir that exceeds the total energy output of thousands of normal galaxies. The random motions of stars within IC 1101 represent one of the largest concentrations of kinetic energy in the observable universe, a cosmic kinetic battery that could theoretically power advanced civilizations for timescales exceeding the age of the universe. The dark matter distribution within IC 1101 creates gravitational effects that extend far beyond the galaxy's visible boundaries. The dark matter halo surrounding this cosmic giant spans distances comparable to the separation between galaxies in typical cosmic neighborhoods. Any object entering this extended gravitational sphere of influence becomes inevitably drawn toward the central galaxy, regardless of its initial trajectory or velocity. So there you have it. When we started this cosmic journey tonight, we were looking at our familiar Milky Way, that gentle band of light stretching across our night sky, home to our 100 billion stars, and the only life we know exists in the universe. But now you've seen what's possible when gravity and time work together on truly cosmic scales. IC 1101, with its 100 trillion stars and 6 million light-year span, doesn't just dwarf our galaxy, it redefines what we thought was possible in terms of cosmic structure. These aren't just bigger numbers we're talking about. They represent fundamentally different physical environments where the very rules of stellar evolution, planetary formation, and even the flow of time itself operate according to principles that have no equivalent in our galactic neighborhood. The next time you step outside and gaze up at the Milky Way, remember that somewhere out there in the vast darkness lies a cosmic giant so massive that it makes our entire galactic home look like a single grain of sand on an infinite beach.